So last time we were talking about barrel shifters, and we got to the point where we had reached kind of some introductory there, and I actually wanted to show what we had. So just as a quick reminder, I brought in our notes from last time. We started off with the idea of a design like this, where we had a series of these multiplexers that would either shift or not shift. The option to choose. Should it shift or not? And they basically went on binary colors, 1, 2, 4. That way you could build any amount of shift from this binary information. And we noticed we could build this type of a setup using the ternary operator, where we said the output, which is, we call it C, just temporarily, the input, we called A, and we said, well, whatever the shift amount of whichever shifter we're at, in this case, shift 0 for the first bit, shift 1 for the second, so on. And then we needed to figure out a shifted, what did that look like? If it's true, we shift. If not, we just pass it through. And we discovered, oh, if we just write this using curly brackets, we can get a definition for B. All right. So using that, we made just a little table. What if we did 1, 2, 4, 8, 16, right? We indexed them and we wrote kind of what our numbers would be. And then we rewrote this, then that same exact operation, now in terms of the double sum being exponentiation. And I said, our challenge is you can't keep reusing A and C here. It's kind of, so we have to be able to figure out what are we going to do in that case. That makes sense. So that's what I kind of gave to all of you to think about. So let me ask all of you, what did you come up with? Okay, so I need something to hold it, right? I mean, in essence, so anything you're doing here, right, is C. Now, in the technical sense, the temporary variable, like you would use in programming, you can't do that, right? Because when you talk about temporary variable in regular programming, what you mean is a variable you're going to reuse in some application. But how do you build something that is temporary or something that's going to get reused? I mean, outputs and things with dumping the same that's right? So I actually have to make for every occasion you're going to need to store something. You have to be exhaustive. You have no choice because there has to be wires to carry that signal that will not later get redefined as something else. Because when it gets defined as something else later, some new thing will be passing into the earlier stages. Okay? So you can't do it in that sense of tempo. But you can use that idea. You just now need to exhaustively enumerate every time it's going to get reused. Uh, this is more challenging, right? So now you have to think, how many times is this going to get reused? Now, my guess for most people's faces is, gee, we did not think about this because class to explain this. Okay, now all the smiles, yes, right? So let me just tell you why that is not. It does not hurt me at all. I know. I came up with this idea like it's many so it's not difficult for me to every update of this. I don't get the one time. It doesn't bother me to have to. But if you don't test your mind, right, you've got to think, how does your brain learn, right? And you ever sit through something that like made a lot of sense, it's kind of cool, you're like, oh, this, oh, I get it. And like 2 hours later, you don't understand it. So, right? It's just reality. Right? You ever drive someplace you've driven a million times and you realize when you get there, you don't remember everything you did on the route and you're not sure what you passed? Yeah, there's a reason for that. Your brain is essentially has efficient memory management. What it does is, if a piece of information is irrelevant to you, it's obvious, it's easy, it's not going to store it. Why waste capacity in some head? Right? Only something that's challenging will actually store that information. Right? That's why when you drive on driven a million times, it doesn't change. Like, I don't need to store this information. It's not that you didn't see it or you weren't paying attention. It's that your brain was not needing to store that information. You've seen those same streets 1,000 times. Why do you need to store it one more time? Right? So your brain is irrelevant. Right? When I make it too easy, right? Any class makes it too easy on you, right? You don't bother to do the reading, which is not fun because you don't know the answer. Any of these situations that are just too easy, your brain is not going to release the chemicals that increase what's called brain plasticity, which is basically the ones that signal, please store this information for me. Okay? I want to make it hard on you, but I want to make it challenging enough that your brain goes, I need to store this. Otherwise, you're going to sit there, you're like, oh, that was a fun class. You explained it really well. And then, like 2 weeks later, you're like, what did you do that day? I don't know, something. Right? And essentially, you will not learn. Right? That's why I asked you to do those little kind of challenging bits. So again, this is not a science thing. This is actually just to think about what you're getting. You want something out of this class. You're spending time, you're spending money, everything else. I encourage you, take the time. When I mention those little things, try the little harder. You'll do one or two things. You'll either figure it out and you'll be very proud of yourself. No, right? It'll solidify the ideas to you because your brain has already released those chemicals. You already start storing the information. You'll get the little fine tunes and everything's good, right? Or you'll discover, my gosh, I don't know how to get to this next step. So it'll be a little bit annoying to you. When you come to class, you're like, I need an answer. That's your brain releasing those chemicals. So you get this, you'll remember it anyway. The reason I have this solutions is to trigger that thing. Whether you get it right or not is actually completely irrelevant. Right? The fact that you face the challenge is what's going to make it memorable. You ever defeat some really tough boss in a video game, and the first time you do it, you're like, think about yourself. You probably remember this thing like 20 years later, right? And you're guy, you remember that. Why do well, it was tough, and you had to figure a bunch of stuff out of how to fit things to do at what times to be able to beat this. Your brain released those learning chemicals because it was challenging, right? So realize challenge is intimately connected with brain. No challenge, no. So, I don't want to make it artificially hard. I want you to make it strategically challenging so that you, does that make sense? Right? So I don't want to lecture this all the time. But I do think every now and then it's a good reminder, spend the time to do it. Right? The only way you achieve is you. Okay. So let's talk about some of these areas. I'm going to give a little bit of creative questions, right? Because I want you to think and give it a shot. Again, don't be sending the remember. I don't, I don't care. I just want you to think about it, create that challenge to figure it out. So we now have the idea. Let's go back to this picture here for a second. Right? Let's try to figure out, or maybe we'll actually draw a new version of this picture, and we're going to figure out goals. So, because the question is, how am I going to do this in a way that I'm going to be able to get some use out of this? I'm just going to do 4 boxes. Is that fair? I'm not going to draw all the contents inside each one. I'm just going to show inside it on one of them. And we know we have 0, 1, and this one just goes straight through. Right? And the other one has some shift, and I'm just going to write shift, assume it's the correct amount of a shift. Right? And I have whatever the appropriate shift amount is. So each of these coming out, right? I have something for this thing that has to do, this is my shift. I'm just going to put SH. This is, my, I'm going to call this in, and I'm going to call this one here. All right. And I'm labeling them inside because that's not what we're going to call them in between, but I kind of want an idea of what each of these actions. Right? So before this was our whatever A, this was C, who are the names, right? Those are not permanent names. It's just to get us conceptually thinking. So each one of these, we have to figure out how to hook them up in between, right? We know that we can, once we have whatever names we want to put there, we can put it into these equations where this in is our A and this out is our C, and here I can just replace them. That make sense? Awesome. All right. So, and then the shift, we've already figured that one out. The shift one is this shift amount, and it's, indexed by I, which will be this for loop. So we can actually, for all of the shifts on here, I can even specifically say this one shift amount 0, and this one is shift amount 1. All right, this is shift amount 2. This is shift amount 3. And we can obviously continue that on this function. Good? Okay. Now, I'm going to add one extra little thing here, right? This is all going this way. So this is the ultimate final. So eventually I'm going to want to send this to the LEDs. All right. And let's call this one the first initial input. Let's say this is going to come from switches or whatever. Right? So I'm just using these names here. We will probably actually, from our board, we won't use the switches. We'll probably have, because we're going to have to reuse the switches and ship them out and switches. So we'll probably use that. But yeah, just to make it think on a page here. So it's grabbing it with me. And then each one of these, it just kind of has to daisy chain between them, right? But when I build them, I might have to build one whole unit inside that for loop. So I have to reference the names here. So each one will need an input and output, which means I'm going to have to name this, and I'm going to have to name this according to my convention. Because every time I walk through the for loop, it's either one block with pig hits. Right? Does that make sense? If I'm going to plot those names, I want whatever convention I pick, the output of the previous stage to be equal to the input to the next stage. So whatever this name is has to be identically the same with this one. Does that make sense as a convention? Now, since that has to cascade down, right? The output is always the input. That's going to suggest that all of these outputs and inputs are going to have one name. Does that make sense? Right? Because since the output, my build is this one, and I have to give this some name here, right? Oh, let's just temporarily say A and temporarily say C here, just like we did before. When I build the next block over here, I've got A and C. It's going to build those same names, right? And this one has to have A and C, and this one would then have to have A and C. Which what does that tell you about A and C? A has to be C, right? Now, can I just pick a standard name? I could standard variables. Okay, they're all A. Yeah, because then what's going if I made them all A's, that's why it's kind of cool to use these variables here, right? They're easy for me to change. Yeah, that means they're all put together too, right? That's why I can't just use temporary. They all be both, so they all short, right? Yes, I'm going to have to make. I'm going to have to make. I can call it index. So now I can go through and I can say, well, I could make this a zero, right? And I could make this one the right side plus one. So this becomes a one, right? So this one has to be what? It has to be a one, right? Ice mistakes. So people don't make mistakes. It's like a mistakes. So these people make the standard restaurants. So they didn't catch up, or then they was it's a fancy or A1. And so that means if I'm always doing this side plus one, that side plus one gives me, this is just a two. I'm going to erase that because who cares? Same sides. All right. So now I can take grade. Well, that works. Right? Say we're doing four, eight, eight, one. So now I've got to think about how big do I have to make A? And A has to be a multi-bit wire whole things, and how many multi-bit operations. I need to have I think it is, a shift about 0, 1, 2, 3, right? How much can this one shift? Massive shift. Yeah. Right? How do you know it's just you know, just so then I A should be bits should be 16. So, I will do one, this will do two, this will do four, this will do eight. Right? 8 plus 4 plus 2 plus 1 is 15. It makes no sense to shift be that 16, 16. That just results in nothing. That's identical to the right? So the maximum shift, and that's something we learned from last time, is the length of when A is in bits. So as a number, I can therefore yeah. So we said we were going to do a shift circuit, but it also doesn't matter which type. If what I have set up here, I can specify I could do a left, I could do a right, I could do arithmetic, which will certainly, it's just going to change which way you do the shifts. Now, the numbers, we're doing shifts. Right? So in this particular case, you go uh, off here. If you look at this, right, this is the right shift. So the number, this is the most significant bit. It was originally on the left side. Now it's been shifted over. If we pulled in all zeros, it would be logical. If we had copied the maximum bit of A every single time over here and then had this, then it would be arithmetic. And in this case, we took the ones that fell off the side and shoved them back in. That's circular. So really, the difference between circulant, logical, and arithmetic is trivial. It's all you're changing. This part right here determines if this is circulant, right? Logical, so I can spell. I would just have all zeros there, and arithmetic, right? Then I would just have A max repeated. Technically, A max minus one. I shift those in. And if we said shifting to the right, they don't need the traction, be a hot shift. So it would kind of be flip of what I had here, right? The circular logical arithmetic, but both logical and arithmetic is just that shifting. There's no sun. So, right. So um, it's in this case, it's pretty straightforward. It's so that the these where they went is your left versus your right shift, right? And what goes into the new evidence? Right? Now I'm doing right shift here, so I'm going to ask you to do left shift. Okay. So we'll do that. Because that's going to be you're a little bit of a challenge. Right? That will also be important that you understand the ideas. Right? So you're going to go in and take a picture, maybe a table, what the shifts look like. You'll get things that will look much like this. They're just going to be going in that direction. And we will keep doing circulant just because it's the most complex case. If you could do circulant, you put series in place and you adjust it. Good.
Yes, speaking of speed, so in this case, the complexity you're increasing it is just like this. You can't use single values to roll them over into the next group. You have to use an array. So instead of space complexity of just operating one, it's the order of 10 things.
Well, it's not exactly. So you're talking, yeah, with a mixed policy, we're talking one to increase for spatial frequency. Right, so that's what he's doing. That's good. We're starting to draw here, right? Uh, if I just had a single shifter that did the whole thing in one fell swoop, right, I would have actually a lot of time complexity to get things. I don't want to have all this extra wires. Right? So that's what we're saying. Just we went in output. But the complexity inside things, right? The time they calculate it gets worse and worse. Right? So in this case, I can say, oh, for instance, I could count how many of these copies. Right? The number of wires is just, if you notice, equal. If you just associate the left one with it, it's equal to the boxes plus one. Right? That's an easy way to figure out how big the array has to be. Is how many boxes plus one. So I saw two hands. I honestly don't know which.
So which box gives you the shift?
Yes. And that's what we were doing. This is exactly this, right? We do a shift by one, we do a shift by two, right? So if you want to do three, you would do a shift by two and a shift by one. If you just want to do it two, you do a shift by two and don't shift, right? So there's a pathway. If you just want to do a shift to one, you wouldn't shift by two and you would shift by one. Right? There's always pass through, as long as you correctly set these, it will let you do any combination. Now, the advantage of this is each one of these is stupidly page, right? So in that sense, it's ask, it's easy, things of that sort. So we like that. It's a nice feature. I think a bunch of these little tumblers. I understand you're kind of calling it a tumbler. You can figure those little twisty things, and there's two groups for you. One that either twisted at each stage, you just say, do I shift or not shift? And you spend up the combination, it shifts when it's done. How many changes though do I need? For let's just count boxes here at the moment instead of wires. Right, since they're at least proportional. Boxes, right, to get wires and boxes. Right? How many boxes?
This this is 15.
So it's going to be 16 number or a number by 16 bits. 0 to 50. I don't forget the Z. That's we only have to go 0 to 1 left. So when I'm looking at this, I can do a shift of up to 16, 15, so I can do 16. I don't delete 4. Square your relationship. Right? I'll take the nut handle. Three of these. So I can have something. I think it's 4 to make. Is 2, basic. It is base 2. So it's not square root, because notice, does that work here? 8 bits and 14. That's what we want, multiple numbers. Because at that stage, at 16, I, first stated, the, the number is 16, but here I've got 8 and 3, right? If I was not careful on here, right, I've got 2 stages up to number 1. Okay, that's right? The problem, the connection between 2 and 4, what's 2 plus 2? What's 2 times 2? What's 2? Then we raise up to, so every time you know, operation 2 equals 4, and the 3 operations we use nicely there. So this is the problem. Data, and why we just do 1 or 2 examples. This is why I went out to 4, because it's kind of confusing when you get out to the big one. It's also a dangerous number, right? But because how does 4 relate to 16? It's 4 squared, right? And it's also base 2, 16. It's also base 2, 4, right? Yeah, so we have to think through this. So what's the actual relationship between the number of pages and how many bits? Long page. That tells me how many stages I actually need. So for my generator, that's what's going to be how often I'm going to have to run that for loop inside that generator. I might have to run once for every longest two make bits. So when I find any right here, right, we're going to do logic. I think the why we want to do logic, so wires or edge or bits. Yeah, because logic is just that, right? If you like wires, like wedges, and you're telling the machine just do, right? It's smart enough to know. There are a few times, but it really, so um, we want that, and we're going to have. I'm going to call this, in this case, I'm just going to say bits minus 1 down to 0. This is however many bits. So if I have 16 bits, then it would be 15 down to 0. So this is just, this is kind of, and we'll come up with something to replace it. So that's actually going to be what we call passing. Yeah, I don't know if we just do capital or something, but most people know that, or size or something of that sort. But this is just for wording. Now I've got A. This makes A to be 16 bits. Bits is equal to 16. But now, yes, A as well as a logic, right? So it function like a wire. This makes one set of 16 bits and calls it A. I this is we just talk about difference. This is making a 16-bit. That's what every one of these individual. I'm going to say 0 to have this many bits. I want every one to have this many bits. It's not big. It makes a 16-bit thing. Now I need to be able to get the 0, 1, 2, 3, 4 thing. That's what comes after. All right? Whatever you put afterward is the this is some of the blues that makes copy like what we see here. And in this case, I want from 4 down to 0. So I can do that. It's technically true. But now place to fix one base. And it's log base 2. I'm going to just write in math notation of bits. That's what's here. All right, log base 2 of 16, 4. It does. It's in a theory that's given to you. Okay, that's what you need to get you go through this. So there is just like did reduce, right? You know, man, like there's a lot of math functions like it's your basic arithmetic stuff, but it really doesn't give you anything else there. So everything else you have to libraries in. So since the database, they can't get a bunch of that stuff. And has been pulled in. So if you have to it, it's kind of automatically loaded for you. In this case, uh, just so you note, it'll be $ C log 2. That will actually give you the log base 2 function. So if you're wondering why the C is in front, that's again from the C math library. Every one of the functions in the C math library has a C. That's just pumping. So when they copied it over into their, they just stuffed in the naming scheme completely. So that's why it comes across that way. All right. So we can actually do this. So I could replace this by $C log 2 bits. And it would actually, we need to do this once. Is just thinking, you could, yeah. So here's what it's going to do, right? So what is going to be a fraction of our game asset? Yeah, so you have to be careful now how you're handling each one of these when you get past it. These are the other things. We want these to be parameters, but not just any parameters. To be something, we're going to generate things, right? If you build as you're going, then it has to be built before you start writing the code. So the generate statement inside this little module to be able to be evaluated before running. That's why you can't pass it in as a number coming in. Right? We use parameter in the sense of fixed thing at the beginning that specifies how to change the module. Whereas it's often used in computer science. Yeah. You got to think of it in variable terms. Parameters are numbers that are available in advance to tell you how to figure it. So, so as opposed to inputs and outputs and in-outs and stuff like that, those ones you only have available during. We cannot use those for a generator because you'd have to wait till runtime to build it, but at runtime you can't build it. You can only evaluate. So let's say this and this. So we're going to need. Now, luckily, Verilog gives us special entities called parameters. which we can specify that will be known before runtime begins. So when it's doing, its initial setup, it will generate everything for you, and then it will start runtime use. But we're gonna have to add these. So to our modules, we're gonna have to do. Does everybody controls modules? Some are saying yes and some no. So we'll talk about that, right? There are three ways parameters can become available to you. They can be global. Yay, right? Global means they're available, visible everywhere. We can also parameters. So we can say, for this particular control, we want you to use a parameter equal to this value for this particular instance. And then you can have local parameters, which are just defined inside the modules and then completely controlled. Right? Now, can we eliminate any of these? Something you should not do unless you absolutely have to. Always don't. Globals. In general, globals should be completely restricted. They should, true, most people use, like, because it's just easy to just define one thing and move on. But the problem is, it makes it really hard to design. Like, if I'm doing a size of one of these modules, I said it's 16, very shifter. Right, and I do it global. What happens if you need one to shift something of size 8? Well, you just ruined that one, right? Because since you made it operate off the global, it will always only ever be 16 in your system. Right? And if somebody needs to change it for something else, it can have something to do with it, right? So global should really only be things like what I typically language and so things like that. That really everybody's gonna use, they do better than change because that's my language definition, things of that sort. So there are places for globals, but it's really small. So for most design things, don't do it now. Right? There are locals and there are things that you can't do as parameters. Do you think there's any better between these two things?
Local is within local and we can't local parameter. So the same thing.
Completely correct. Yeah, that's exactly it. So in this, there are cases where I can use local parameters if I'm going to do something that's like 20 great call. But in our case, we want to build something, right? Which means it has to be available before I'm going to this character to use it to build. Right? But you don't get the local environment until you build the module. Therefore, it's too late to actually generate. You cannot use local parameters for it. It will fail because it's just not available. You need it to be. And if they don't get it, to be all that. Right? So remember, the generate is not regular code. It's telling you how to build the code. So it has to be available before the local context is making the local context, or at least. So you have to have to. So that's going to be our big key. So when we do these, we're going to need both the low-based version and the full size of the version. We have to put both in the package. Yeah.
Okay. It's just the same length format of our like.
So if I were to come in here and do this by hand, right? That's this one here, right? We could call this module, right? We declare it, right? And I need, I'm going to make a barrel shifter, so we'll call this BS, right? Break in for barrel shifter. Okay? So module BS, and I want to do parameters. Anybody remember how I specify parameters? Yeah, but now parameters are different than ports. So I need a really sharp idea of how I can make this different. Yeah, you have a sharp hashtag, right? So this one tells you you're about to do parameters. Now, there's a lot of different ones that you can actually pass besides parameters. We're only at this point ever going to care about parameters. So right? Parameter, and then I could say, for instance, whatever we want, n, right, is going to be my size, and I set a default. Like, let's say I just say, I don't care, you can use size, you can do whatever, I'm just lazy and just want to type one, right? And then I'm going to make another one that's log 2n, right? That's actually just a name now. And its default thing is going to be $, and we do C log 2 of it. Fine. So it's just after the equals is the default. So I can change these using that application. So if I say, for instance, .n equals 16, when I do reassign to it will therefore calculate log 2 $C log 2 of 16. Right? So that's the nice feature about this. As long as you don't redefine C log 2n, right, you only change on your parameter coming in. Change the style. Yeah, anything inside this that, and then you can. So when you make an instance module, right? Yes, I would tell it BS, right? And I'd have to say hashtag and then dot and I could say like 16. Because remember, all of this, right now, this is all you, right? When you do it, you have to in the BS with this arrangement, right? That's the thing you want to do. That completely specifies what you want to do. And then I can give it, a name here, whatever, BS, right? Big definition. So it to whatever the specified build is, right? Whether that's a variable type, that's like the parameter information for the name. If you get this, it's going to be really confusing. Whatever is left of the name tells it what to build. Anything so that it does customizations. And left is intent, right is untapped. Lots of ways to think about it. Fair? And then afterwards, right, I then have a second set of parentheses, and now I can specify my points. Right? So at this point, I can now do whatever my inputs and my outputs and whatever, right? So in this case, we have input, and I don't want to be constrained to anything like a wire might, so I'm just going to force it to be a logic here. And then I'm just going to do n minus 1 down to 0. So again, I can now use this parameter here. All right. So I'm saying whatever's coming into me as logic, my input has to be in bits long. So this here, and I'm going to call this in, for lack of a better name. Right? And I'll have an input. Again, we'll do logic because then I'm free to use it however I want. Right? Now I have to do log 2. Because remember, the amount that I'm going to be using as a shift is not proportional to the bits n, it's proportional to the log base 2 of size. So this will be log base 2n minus 1 down to 0. And that is how big is my shamt from what we've been using so far. All right. And then I'm going to have an output. Again, I'm going to do logic because it just makes my life easy. It's got to be the same size as the input because it's just a shifted around version. And I'm just going to call that out. All right. Now I have a complete definition of whatever I'm doing to build this thing. That specifies the module. So when I go here for this, I'm now going to have, and I often just do this pretty packed here. Uh, but when I get to this point, I'm going to want to do dot in, and what do I want to make it? Right? What am I going to pass to it? And dot shamt and whatever I want to pass to it. Dot, just comma list. Um, and then out, dot out, and whatever it is, and now I'm done. Right?
So for our inputs, you're saying that so for the instantiation here, you have to do this and add in logs to it. Is there like these are inputs? Is there enough here to make all the states? Like can you have the states that input?
What do you mean by state?
Well, okay, so there's like the branches for like in like programming. There's like callbacks where you have then you have inputs and then also the current state of your then you can see that you're
So we have to figure out how you're building it. So in the general sense of state, right? Most computers, your current state is handled typically by stack, probably the stack plus the heap. And sometimes in those ones, I can always call out to. And I also have a state which is, there are um, general purpose registers, your, which hold variables, but there's also special purpose one, which holds state information, like my last arithmetic operation. Did it do a divide by zero? All these those are held in what's called special purpose registers. And I can pass those special purpose registers also. That's in regular programming. Um, Generally speaking, we have to think about what do we intend for these ones? Do we want them to have memory? That's what they're going on. And there are a couple other things that we could do with these, but generally we're thinking does it have memory? In this case, a barrel shifter has no memory. Right? So this is more like a function, right? So it technically has no state as far as we're concerned, because the output is completely uniquely determined by the inputs. So nothing else is needed. So in this case, it makes sense, right? If I had some type of memory, uh, and I was doing a memory in here, then I might pass some extra information, resets, and other things like that. So you know the information that I'm typically extremely limited to what you specifically need. You don't want to list just everything. Because think about it, if I list everything, the machine's going to have to pull those signals in close to this box. So we're going to sort of use these port lists and everything to tell it what needs to go near you when it tries to basically plan them. So not listing unnecessary things is very helpful to us. So those are good questions. Does everybody feel comfortable with this? So the lower one here, right, the module VSL, this is go in and telling you, this is my list of ports, parameters, right? That's the basic, what we call an interface to this system. The other one, the lower piece of it is an implementation, right? Or technically an instance, right? So it is being you built. I have tons of, but I only have one interface on description of how. So in this particular case, we gave this interface that that's what's going to pass things. That's the outside of the line, right? And then we said fill the box.
So the goal of the graph is to resolve to generate function.
Yeah.
So and build a long product the information that they want to be make it a take other within the gen bar and followed by the logic of this way.
We're going to put the gen bar actually inside this module. it'll call the generate function and build it for me, right? And the one that's doing the instantiation up there, to give it enough information to run the generate function that it needs. And when we have to find it, it'll also automatically count log base 2.
And the also do conventional as it pushes over
Yes. It's all on compile time. Not an ease.
conventional. This is also a question.
So generally speaking, our convention is going to be put each module in its own individual file, unless it's not standalone. So if you're, as a user, are going to use it, it should be in a file with its name, right? So I'll make a separate file, bs.sd, right, in this case. Because then when you're looking for it, you know the module name, you can find it. And also makes it quicker. The interpreter is looking for it and wants to do that compilation process, it can find the file looking for the module name with the .xd or the .d on the end. If it is only associated with this, like you could make small modules that then build this up. I could, if it's only using it, I could put it in the same file. Because then the second you grab this, you can. But if some little builder part of it underneath it, like let's say the need of a full for some reason, but I might use that full adder in other places, then I should put a full adder in a single file and say, does that make sense? This is the same convention MATLAB uses. So MATLAB doesn't want you to do anything else, but if you don't call it function name, it's going to be happy with applications. It wants to have that name because that is a scripting link. That's how it quickly finds its files inside. Doesn't it make it a ridiculously big thing? Yes. But would you ever get all that? Yes, baby. Right? But then you're going to suffer with that. Right? So if I want to actually do this, I can compile this. And you compile it into a library package, and then it bundle. That's generally the convention of most of these text language ones. If if you're going to yeah.
So this module, it's like, would be one of the squares, so this is, we got 4, or is this the entire?
Inside this module, it's going to do the whole output. Right? That's why we're pensing this. It's going to go inside that generate function. It's going to know how to do each of the functions. And it's actually pretty short, a few lines long, because generate is very powerful. In order to use that, we have to do a lot of tools. Then, once you get this part, really, there's only a few lines of this, and you're done, right? So, leave some blank space here because we have to put in the, well, we can do the first part of this. Let's do the A variable, right? Is it okay if I just call this A like we've been doing here? I'm gonna stick this. You don't need to see the how do we build it stage here, right? So I need to put this now inside my function, right? This is all the stuff. Now I have to say, how do I do this? What makes BS, right? So I've got logic, and now I've got to, again, A has to be the same size as my inputs and outputs. So it's also going to be an n minus 1 down to 0. That's how big A is. It's going to be a bunch of these logics, right? This is a bit array. That's what A is. But I don't just want one of them. I'm going to reverse my direction. And the reason I'm going to do that is just to make it a little bit easier. I'm never going to deal with these in full. I'm going to do them separately. But this also lets you know I can go in either direction. So I'm going to go up to, and I need from 0 up to log 2 of n of them. Right? So this says A is an packed array of these, and then give me 0 to these, which is, since it's 0 up to log 2 of n, it'll give me log 2 of n plus 1. Because we're going to start at 0. For the wires, I needed one more than log base 2. Yay. So put the minus 1 here. But this gives me essentially with, if n is 16, this is 4, so this will give me 5 of these wires. That'll be numbered 0, 1, 2, 3, 4. Does that make sense? Awesome. So now I've got my n, right? And we made the statement that I wanted this to be hooked to whatever. In this case, I called it in, right? And I called the other one out. So I've got to hook A0 to out, and I've got to hook this last A to in. How do we connect two names in the sign statement? So we're going to do a sign, and I want to get whatever my names of these are, right? My say we set output. In this case, we set it to whatever A0, right? Um, and we set proven I'm dyslexic and reverse letter readers. Now this time, right, I want A4 to get in, right? But A4 is actually could change based on my number. So I have to specify it as A log to N, right, is equal to my input. Fair? So if N is 16, what's log 2? 16. 4. So this would say N4 is equal to the input. One of them should be 0 and one should be your biggest number. And your biggest number is based off the log of this, right? And I'm not specifying the individual bits they're counting. So you'll get the whole group of 16 of them. And at this point, this logic of 16 bits is now just functioning like you can't plug it's just the data type. It's a array of logical wires. Good? Right? Because this is the type of stuff I would expect you'll be able to do. That's why I want you to understand the ideas. And I'm laboring it now, so I won't have to labor it later. All right. At this point, I've defined all the names. Now all I have to do is do my generate function. So first, I need a gen bar loop index to walk through. Right? It's not going to actually be built. Gen bar just means this is an index that I can use to decide how many times to build something. So it's something just used in the building process. And then we can start our gen. Yes. Gen I and then semicolon and then generate, right? So generate says build something, right? And it'll be end by an n generate. Now inside here, I just build my for loop. And we already actually talked about this last time, right? But we have to swap in our variable names, right? So if you remember, we just had this for I, right? We had gen bar I, right? Generate, for I, right? All that kind of stuff. But now this log 2 of max, I have log 2n, right? So I'm just going to stick this off to the side because it's really hard to hold here. And we'll just write them out, okay? So we're going to do a for loop. And I need my I to start at 0. And now I want my I to build up to whatever that log 2 size is, right? So I less than log 2 n, and then I plus plus. Fair? Now, there's only going to be one line in here, right? And this is going to look weird because remember we said never stick an assigned statement inside a procedural block. Doesn't this look like I'm sticking an assigned in a procedural block? Except you're not, because it's not a procedural. A generate function is just a machine to build things. So inside this for loop, I'm saying, well, what should I do? I'm literally inside. Imagine it's going to be put in the file. Right? I'm telling you, what one should write is a statement statement. So we're going to go a bunch of these based off the form. So that's all that's happening. There's only going to be one of these. I am going to name this though. And I want to name this assigned statement. So the only way I can put a name on this is if I put a name, system Verilog allows you to put a colon and then I could put a name. So for instance, I could call this the tumbler. I run the tumbler and the log, each stage tells me do I shift or not. So I can say a tumbler. Since this is going to be a recording, it's going to make an array of tumblers that will be indexed by gender, the I. So we'll get tumbler 0, tumbler 1, tumbler 2, and that way I go, when you choose things, and then the name will appear in the simulation. So when I look at the simulation, that's the one that ships by the tumbler 1, and I know that's the one that ships by 0 2. Right? So it's for this day. It's just for readability in the test bench. Because then if you have a bunch of these, trying to tumble switch is pretty hard. If you have a name, because it's not even against it, humble. I have this statement, just you have this statement with all these agreements. That's not readable. So this way I can put a name on whatever is inside. And the only way I can do this is with a begin statement. So while I don't need a begin statement because there's only one line in here, I need the begin statement because it's the only way I can name it. So this will therefore have an end also. Does that make sense? So we've got our assign statement. Now we want to assign it to it. And we're going in our case, right? The n, the output is the lower number. The input is the higher. Does that make sense? So I'm going to say assign, in this case, a sub I, the lower index, is going to be equal to, now I need my ternary operator, right? The shamped I, that will tell me the particular index, should I shift it or not? Ternary operator, was this true or false? If it's true, I should do the shift. So now that's where I want this lovely little convention here, right? So I'm going to have the curly brackets, and now instead of just A here, this will be the A I plus 1, right? This is that right side, which is the larger number. Make sense? So I'm going to have that, but then the rest of this will be identical, right? I just have to replace all the A's here by A to I plus 1. Okay? All right. So, what's up? Then, because it's going to do all of them before it runs. This is all in essence, pre-run time. Right? So the first thing Verilog does when you start to run it is it goes through and it finds out, is there anything I need to build? It makes all its little tables, it loads everything in, Initially, it does that by pushing it on the staff. So technically speaking, it's very religious. The last should be pushed, right? That's at build time. So it kind of does it get shorter, but it will actually, because it pushes all staff and it builds systems. So it does, when you run through some ways you can do it, every time you find something to build, it pushes it onto the staff. It goes through it from all of its files, everything it needs to build. And then it helps. And it's much easier and everyone's operating. So it typically actually goes. But it's irrelevant. You're not going to know it does it before. But that is actually the order. Sometimes it helps to debug, but sometimes it screws up a little bit. It happens. All right. So inside curly brackets, remember curly brackets appends. So I'm going to have this, which will be only plus one, take it from the slightly bigger one. And then I literally just copy that number. I'm just going to literally copy it from the sheet next to me to save myself time. 2 double star I minus 1, 0. All right. So that one gives me, right, everything of this, right? This is all the wires from this one, comma, append them with, I have to go to the next line. All right. So technically this would be one long line, but I'm just going to just continue it down here. All right. And then I do the other side, right? So this was what was on the right. Now I have what was on the left. All right, so that's going to be whatever my n minus 1, that's my leftmost bit, all the way down to 2 to the i's power. 2 star star. And those all get appended together. Fair? That is just literally this that I just copied over. All right, open bracket, 2 star star I minus 1 down to 0. You can see there, comma, I didn't have enough room, so I just carried the line down. Right now, I'm replacing A by AI. Oops, AI plus 1. Because I just had an A there. I forgot to add my plus 1. It has to be the same as this one. Right, the input stage. All right. And then, we had been calling it max, so I just replaced it with N since that's our size variable. N minus 1 colon 2 star star I. Right? And then colon, this is the continuation of my question colon. Right? This is what if it's false? Well, then I just give it AI plus 1. I don't need to mess anything up. I just give it AI plus 1 and I am done. All right? That is all I need for my generate statement. So I end generate and I end the module. All right? And that is all I need. That's a completely functional model. The biggest stupid barrel shifter, all these barrel shifters, and you can obviously modify this to make whichever, right? Modify the assigned state instead of generate. Even whatever type of shifter you may certain electrical or magnetic, just change this define. That's the only difference. We only have we typically that's what
For this case, we only use them because we're using.
yes. And from that again, it's like looking in place for other practice. Right? You don't tend to do the closing and see. You don't get to do the beginning. It's only one. But if it happened again, I wouldn't be able to do that whole and then give it a name. Give it a name. So I'm kind of stuck putting the beginning in. You can curly brackets is put the beginning in. Generally, it's harder to read a thing there, just because it's ugly stuff. That stuff is cool, right? But having that simulation, so I'll take a look at this here.
begin at, so we'll get the date, right? And the complexity when you do a simulation, you just see.
Do we feel good for this? So you, I think you've got this basically done, right? And you've got the initiation. Can you make a prediction on BS? Right? So maybe you want to look at BSRs, right? BS rate of BRC, right? BSRC. You know, a single shifter, because that's what we built inside. Can you make a BS number standard? This will be your way of thinking. Did you understand what I did? If you can build BSLC, you understand what I did. I, I try to basically leave myself on this. I try to do it without looking at it. Again, the learning thing, if you try to do it without looking at it, you know, forward your brain to do the stuff that doesn't to recognize what stuff did it make sense, right? And then you can look at it and try to figure out, oh, that's it. That's how you can, your brain will be, oh, and just bring that in. It's one of the best ways for. I've done other methods. This one is kind of a reinvention style where you um, where you're trying to basically pull it back up and go for rewards for getting the answers. And you got the answer next to it. Make sense? Okay. So do that next time. We'll build and talk about how we can do testing next time. And then you should have everything you need and you can formulas and your personal all this stuff. Right? Everything else is going to completely be like this. But just depends how much I actually do paying for you and how much you do. I end up getting a little complicated. Right? Because it's just a lot of money. Right? But if you get how to do this, you have the foundational stuff you need. Because we'll do a bunch of generates and do the same. We good? Actually, 30 seconds early. Somewhere between 30 seconds. But we're within that metaphor. If anyone has any questions on that, we can figure out if it's. All right. Well, I'll let everybody know if you got questions, you know, come up and hand on me, and I'm happy to answer. Otherwise, have a lovely day, and I'll see you on Thursday morning.